Hello my dear students, welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous module, we have discussed the waves and various wave propagation parameters. After the discussion on wave propagation parameters, I have introduced you to the principles of electromagnetic waves and then discussed the propagation characteristics of electromagnetic waves. They are alpha and beta. And then I have defined a propagation constant gamma which is equals to alpha plus j beta. And I have told you that alpha is called the attenuation constant, which tells us how much does a wave get attenuated if it travels per unit distance. The units of attenuation constant are either decibels per meter or Napier's per meter. And then we have discussed phase constant. It tells us the amount of phase shift a wave experiences when it has traveled for unit distance. And its units are pretty obviously radians per meter. So these are the propagation characteristics which we have seen in the previous lecture. In the current module, we would continue our discussion on electromagnetic waves. In our discussion on electromagnetic waves, the contents we would be covering are various modes of electromagnetic wave propagation. And then what are various types of electromagnetic waves? The common types of waves we will be discussing are spherical, cylindrical and plane waves. Once I discuss these three different waves, then I would say how a spherical wave can be approximated to be a plane wave. And after the discussion on these types of waves, I would discuss a special class of electromagnetic wave called as uniform plane transverse electromagnetic wave. And then I would define intrinsic impedance. This is one more propagation parameter of EM waves, and it is also a medium specific quantity. And then I would discuss Poynting theorem, which discusses the flow of energy in EM wave. It is better to recollect that waves by nature are means of transfer of energy. Now, how does this transfer take place in case of electromagnetic waves is discussed by Poynting theorem. So, let us start our discussion on modes of electromagnetic wave propagation. These modes of electromagnetic wave propagation are characterized by the directions of electric field intensity, magnetic field intensity, and the direction of electromagnetic wave propagation. If the mode of propagation is transverse electric mode, TE stands for transverse electric mode. If this is the mode of propagation, then the direction of electric field intensity is always perpendicular to the direction of propagation of electromagnetic wave. That is, if the electromagnetic wave is propagating in this direction, electric field cannot exist. Similarly, if it is the transverse magnetic mode of electromagnetic wave propagation, in that the direction of magnetic field intensity is always perpendicular to the direction of EM wave. So, if this is the direction of EM wave, then this can't be the direction of magnetic field intensity. The mode of EM wave propagation is transverse electromagnetic wave, In this transverse electromagnetic mode of waves, both electric field intensity and magnetic field intensity are absent in the direction of propagation of electromagnetic wave. That is, if this is the direction of EM wave, then along this direction neither electric field nor magnetic field can exist. You may recollect that from Maxwell's equations, it is clear that E bar and H bar are mutually perpendicular. Now, in case of transverse electromagnetic waves, E bar and H bar, which are already perpendicular, are also perpendicular to the direction of electromagnetic wave. So, in other ways of putting, the direction of EM wave propagation is always along the normal to the plane containing electric field and magnetic field. In this course, we will discuss only this kind of waves. This transverse electric mode and transverse magnetic mode are discussed when we discuss waveguides, and which is not in the scope of this content. Therefore, in this course, we will discuss only transverse electromagnetic waves. Their E bar is perpendicular to H bar is perpendicular to E bar, and H bar is also perpendicular to the direction of electromagnetic wave propagation. E bar is also perpendicular to the direction of electromagnetic wave propagation. So, what are various types of waves and how do they come to their shape? These types of waves are classified according to the shape of phase front. The word phase front is combination of two words. If I split them, the last part, the front part, corresponds to the collection, and phase corresponds to constant phase. So collection of points which are having constant phase is called as phase front. So the types of waves are classified according to the shape of these phase fronts. In this class, we would see what are various phase fronts available. So phase fronts are the shape formed by surfaces in which all the points have equal phase. The phase fronts attain their shape because of their source of radiation. Whatever is the source of radiation, that gives the phase front their shape. When the dimensions of source are very low compared to the area in which the wave is being analyzed, as we have seen this many a times, if the physical dimensions of the source are negligible compared to the area of interest, then that source is considered to be a point source. Now, if I have a point source, then this is how the phase fronts take place. The phase fronts will take the shape of concentric spheres. So this is sphere 1, sphere 2 and sphere 3. In other words, the phase is dependent on the radial distance from the source. If the phase is dependent on the radial distance from the source, then they take the shape of concentric spheres. Now, all the points which are having same radial distance would always form a sphere. Therefore, these waves are called as spherical waves. Spherical waves are formed by point sources. If only the length of source is comparable to the region of interest, you may identify this if only one dimension of the source is considerable and all other dimensions are negligible, then such sources are line sources. So if I have line sources, then generally the phase of electromagnetic waves is dependent only on the perpendicular distance from this line. So the collection of all points which are having same perpendicular distance from this line form cylinders. So this would be how this radiation takes place for a line source. These waves whose phase fronts are cylindrical in shape are called as cylindrical waves. And the next class of waves is when I have a parabolic source. For example, say a parabolic antenna. So if the waves are radiated by parabolic antenna after some large distance, the phase is dependent only on the perpendicular distance from the source. If this is the perpendicular distance from the source, the phase are dependent only from the perpendicular distance from the source. If I collect all the points which are having same perpendicular distance from the source, then they form planes. Therefore, these class of waves are called as plane waves. So plane waves form parallel planes. The phase fronts are parallel planes like this. The phase on any plane, plane 1, 2, 3, is dependent only on the distance traveled by EM wave. Because see, this is distance 1, distance 2, distance 3, and these are what differentiating these planes. Therefore, the phase is dependent only on the distance an electromagnetic wave has traveled thus far. As I have told you, we will discuss planar approximation of spherical waves. Why do I need to discuss this is because spherical waves are most common kind of waves. Because point sources are most prevalent. That is, the dimensions of the sources are generally negligible when compared to the region of interest. Therefore, by nature, we have point sources in abundance. Therefore, spherical waves are most common kind of waves possible. After considerably large distances from the source, portions of the spherical phase fronts can be approximated as planar phase fronts. So this plane is one plane and this is another plane and this is another plane. On a same sphere, I would have multiple planes. And why do I do this? Because it is obvious that analyzing a plane wave is much more easier when compared to analyzing a spherical wave. Because a plane wave is dependent only on the distance an electromagnetic wave has traveled. And this concept is nothing new. We have already seen this. In fact, we experience this every day. Imagine that this is the Earth. Earth, in absence of its irregularities, can be approximated to be spherical in nature. And any person who is living on this region feels that Earth is flat. Similarly, any person who is living in this region feels that Earth is flat. Similarly, any person who is living in this region also feels that Earth is flat. So anywhere you go, you feel that Earth is flat, but in fact, Earth is not flat. Earth is spherical in nature. But that may not be felt if the wave has traveled for considerably larger distances. So this approximation of a spherical phase front to planar phase front is called as locally planar approximation of spherical waves. And I do this to simplify the mathematical analysis. Now, I would discuss a special class of electromagnetic wave called as uniform plane transverse electromagnetic wave. In this kind of waves, electric field and magnetic field are mutually perpendicular. For any EM wave, electric field and magnetic field are mutually perpendicular. So there is nothing new here. But the direction of propagation of EM wave is perpendicular to the plane containing electric and magnetic fields. In other words, the direction of EM wave propagation is along the normal to the plane containing electric field and magnetic fields. And then phase fronts are parallel planes. From the concept of plane waves which we have seen just now, the phase fronts of plane waves are parallel planes whose normal is along the direction of propagation of EM waves. And you may have also seen that the distance travelled by this EM wave is the only factor which is changing the phase at any phase front. And the magnitudes at all points in a phase front are equal. This corresponds to the uniform nature of the waves which we are discussing. So if I have a phase front, by definition, all points on this plane have same phase. That is by definition of a phase front. But when I come to a uniform plane wave, when I am talking about a uniform plane wave, at any point on this plane, the value of electric field and magnetic field are constant. That is the meaning of a uniform plane wave. That is, not just the phases, the magnitudes are also constant. So this concludes the introduction on uniform plane transverse electromagnetic waves. Let us see how this affects the nature. Please note that every point is color coded according to the reason of their existence. If I assume that electric field intensity is along AX cap, then the magnetic field intensity can either be along AY cap or AZ cap, but let me say that it is along AY cap. If it is along AY cap, then from the nature of transverse electromagnetic wave, the wave propagation would be along plus or minus AZ cap. And I can say that the direction of electromagnetic wave propagation is given by E bar cross H bar. So if E bar is along AX cap and H bar is along AY cap, then the direction of electromagnetic wave propagation would be along AZ cap. And if the polarities of the direction change, then the corresponding direction of the electromagnetic wave propagation change. The phase of wave is dependent only on the distance travelled. The distance travelled is along AZ cap. That means phase is a function of Z. Similarly, because the magnitudes at all points in a phase front are also equal, therefore, the magnitude of E bar and H bar are also dependent only on Z. They are not dependent on any else. They are not dependent on X, they are not dependent on Y, but they are just dependent on Z because of the uniform nature of the uniform plane transverse electromagnetic waves which we are discussing. If the electric field is along AX cap, then the phasor of the electric field would be of the form EP bar is equals to EXP AX cap. The suffix P indicates that this is phasor form, and AX cap is the direction of electric field intensity which I am assuming, and EX corresponds to the component along AX cap. But we have already seen that EXP can be only dependent on Z. Therefore, EXP is a function of Z. Similarly, the phasor of magnetic field intensity will be of the form HYP AY cap. Again, HYP can also be a function of Z because of uniform nature of the plane wave. So these are the phasor forms of electric field intensity and magnetic field intensity. Let us see how the wave would appear with respect to time. To do that, let me use the vector wave equation which we have discussed in the last lecture. So this is the expression of a vector wave equation. So if I expand this Laplacian operator, I would be getting this. I could further expand this to be EP bar is equals to EXP AX cap. By substituting this, I can further expand this equation to this form. But as we have discussed, exp is just a function of z. It is not dependent on x. Therefore, there would be no variation with respect to x. Similarly, it is not a function of y. Therefore, there would be no variation with respect to y. But this is a function with respect to z. Therefore, this remains. So, this differential equation can be simplified to dou by dou z square minus gamma square of exp ax cap is equals to 0. So if we are talking about only the physical quantity exp, I can rewrite this dou by dou z square minus gamma square of exp is equals to 0. If I solve this partial differential equation, the solution to this differential equation would be exp is either E naught exponential of minus gamma z or E naught prime exponential of gamma z or the combination of both. But exp would take E naught exponential of minus gamma z when the wave is traveling along az cap. Similarly, when the wave is traveling along minus az cap, then exp would be of the form E naught prime exponential of gamma z. The logical explanation behind this is, if the wave is traveling along az cap, then the intensity, if it falls, is going to fall. It cannot raise because the source is at 0. You cannot have a higher energy than source. Therefore, it is going to fall. Now, if it is going to fall, exponential of minus gamma z needs to be less than or equal to 1. This cannot be greater than 1. For this to be not greater than 1, z needs to be always positive. Therefore, if the wave is traveling in positive z direction, this would be the expression of the phasor, and if the wave is traveling in negative z direction, this would be the direction of the phasor. Right? Now that we have obtained the component of EP bar along AX cap, let us also try to determine what is its time variant version. So now that I have exp is equals to E naught exponential of minus gamma z, I can write EP bar to be exp ax cap, that is equals to E naught exponential of minus gamma z ax cap. But you remember that gamma was equals to alpha plus j beta. So exponential of minus gamma z can be split into exponential of minus alpha z times exponential of minus j beta z. Now that I have obtained the expression for phasor, the time domain expression of electric field intensity can be obtained as the real part of phasor multiplied by exponential of j omega t. So if I multiply this with respect to exponential of j omega t, I would be getting E naught exponential of minus alpha z times exponential of j omega t minus beta z along the direction of ax cap. And if I take the real part of it, because these are purely real, I can take them outside before real part of exponential of j omega t minus beta z along the direction of ax cap. But exponential of j omega t minus beta z is cos omega t minus beta z plus j sin omega t minus beta z. The real part of it is cos omega t minus beta z. Therefore, if I take the real part, I would be getting E naught exponential of minus alpha z times cos omega t minus beta z along the direction of ax cap. So this is the complete expression of electric field intensity for a uniform plane transverse electromagnetic wave. See, in this, both the magnitude and the phase are purely dependent on z but no other space. That is, it is not dependent on either x or y. Similarly, if I do the same analysis for magnetic field intensity, I would be getting that dou by dou z square minus gamma square of hyp is equals to 0. Therefore, hyp would be equals to h naught exponential of minus gamma z or h naught dash exponential of gamma z. Again, if the wave is traveling along az dash, then hyp would be h naught exponential of minus gamma z, and if the wave is traveling along minus az cap, it would be h naught prime exponential of gamma z. From these phasor expressions, I can also get the time domain expression to be h naught exponential of minus alpha z times cos omega t minus beta z. I have got the result directly. If you want to do this analysis, I suggest you to do it on your own because it is pretty similar and along the same lines. Now that I have obtained the expression for electric field intensity and magnetic field intensity for a uniform plane transverse electromagnetic wave, let me define another wave propagation parameter called intrinsic impedance. The intrinsic impedance is the ratio of magnitudes of electric field intensity and magnetic field intensity in a medium. So it is magnitude of E bar by magnitude of H bar. It is denoted by eta. So eta is equals to mod E bar by mod H bar. We have obtained that E bar to be equals to E naught exponential of minus alpha z cos omega t minus beta z along the direction of ax cap. Therefore, the magnitude removes the ax cap, and similarly, the magnetic field intensity to be h naught exponential of minus alpha z cos omega t minus beta z along the direction of ay cap, and the magnitude removes the ay cap. Therefore, this is what we get. Out of this, exponential of minus alpha z cos omega t minus beta z is common. Therefore, the intrinsic impedance is E naught by H naught. Let us try to determine the value of intrinsic impedance. I know that del cross EP bar is equals to minus j omega mu times HP bar. This is the Maxwell's equation in its phasor form. So from this, I can always say that HP bar is equals to minus del cross EP bar by j omega mu. So if I substitute that EP bar is equals to E naught exponential of minus gamma z along the direction of ax cap to this equation, I get HP bar is equals to minus curl of E naught exponential of minus gamma z ax cap divided by j omega mu. But curl of any vector field is given by this. Here we are trying to determine the curl of EP bar. But the formula of EP bar is E naught exponential of minus gamma z along ax cap. That is, it is just exp ax cap. That implies EYP is equals to 0 and EZP is equals to 0. And not just that, EXP was a function of Z. It is not going to vary with respect to either X or Y. Therefore, because AZ is equals to 0, this would be eliminated, and because AY is also equals to 0, this would be eliminated. This is eliminated, this is eliminated. The only remaining terms are dou AX by dou Z AY cap plus minus dou AX by dou Y AZ cap. But this AX we have is only a function of Z. It is not a function of Y. Therefore, this would also be eliminated, because the curl of E naught exponential of minus gamma Z has been just limited to dou by dou Z of E naught exponential of minus gamma Z along the direction of AY cap. And if I differentiate this with respect to Z, I would getting minus gamma E naught times exponential of minus gamma Z along the direction of AY cap. That is the value of curl. But HP bar is equals to minus curl by J omega mu. That we getting is equals to gamma E naught exponential of minus gamma Z divided by J omega mu along the direction of AY cap. So this value at Z equals to 0 is H naught. So H naught is equals to gamma E naught by J omega mu. If you remember the definition of intrinsic impedance, the intrinsic impedance is equals to E naught by H naught. So this is equals to E naught divided by gamma E naught by J omega mu. So this would be equals to J omega mu by gamma, but we have gamma square to be equals to J omega mu by sigma plus J omega epsilon. I can write gamma to be root of J omega mu by sigma plus J omega epsilon. Therefore, eta would be equals to root over J omega mu by sigma plus J omega epsilon. So this is the value of intrinsic impedance experienced by uniform plane transverse electromagnetic wave. Please do these calculations of yours. Determine gamma, alpha, beta and eta of a wave in lossless dielectrics, free space, perfect conductors and also imperfect conductors. The meaning of imperfect conductors is that sigma is not equals to infinite, but sigma is a very high value. In this, you would be introduced to another concept called as skin depth. So I suggest you to please do this on your own. So let us conclude our today's module by discussing Poynting theorem. Poynting theorem discusses the amount of energy leaving any closed surface. So the amount of energy which is leaving any closed surface along with an electromagnetic wave can be obtained by the closed surface integral of E bar cross H bar. Because as we have seen already, E bar cross H bar is the direction of EM waves propagation. So the amount of energy is the closed surface integral of E bar cross H bar. Let us see and how this E bar cross H bar's closed surface integral can be obtained using the Maxwell's equation. If I consider this first Maxwell's equation which I have written here, it says that del cross H bar is equals to J bar plus dou D bar by dou T, but this can also be written as del cross H bar is equals to sigma times E bar plus epsilon times dou E bar by dou T. If I dot both sides of this equation with E bar, I get E bar dot del cross H bar to be equals to E bar dot sigma E bar plus E bar dot epsilon times dou E bar by dou T. The result of this dot product would be sigma E square. E square is the mod E square plus epsilon times dou by dou t of mod E square. But from vector identity, the divergence of cross product of any two vectors is equal to the second vector dotted with the curl of first vector minus the first vector dotted with curl of the second vector. So from this, I can obtain that E bar dot del cross H bar to be equals to H bar dot del cross E bar minus the divergence of E bar cross H bar. Let me show you that here. From this vector identity, I can write the left hand side of that equation to be H bar dot del cross E bar minus del dot E bar cross H bar. But this we have obtained from the dot products here. But we also have del cross E bar to be minus mu times dou H bar by dou T. If I substitute that here, H bar dot minus mu times dou H bar by dou T minus the divergence of E bar cross H bar is equals to sigma E square plus epsilon times half dou by dou T of mod E square. So this is what we have. Again, if I dot this, I'd be getting minus, this would be minus mu dou T by dou T of mod H square. So this equation I can be writing as the divergence of E bar cross H bar. If I take the negative sign there, the divergence of E bar cross H bar to be equals to minus sigma E square minus epsilon times half dou E square by dou T minus mu times half dou H square by dou T. If I take the volume integral on the both sides of the equation, I get volume integral of del dot E bar cross H bar is equals to volume integral of minus sigma E square and the other terms as followed from the above expression. But you may see this is a very prominent result we have used in divergence theorem. Now I am just applying the inverse of the divergence theorem. I am going to obtain the closed surface integral of E bar cross H bar from the volume integral of divergence of E bar cross H bar, because the divergence theorem says that the closed surface integral of any vector field is equal to the volume integral of divergence of that vector field. Now the vector field in question is E bar cross H bar. Therefore, the volume integral of its divergence can be equated to closed surface integral of its E bar cross H bar. So I can write that to be this. I can rearrange these time differentiations together and I can write the closed surface integral of E bar cross H bar dot ds bar to be equals to minus dou by dou T of the volume integral of half epsilon E square plus half mu H square minus volume integral of sigma E square dV. The meaning of this expression is the amount of energy which is leaving any closed surface because of an EM wave propagation is equal to the decrease of the energy stored in electric field and the energy stored in magnetic field minus the ohmic losses. This is called ohmic losses. This exists because of the conductive nature of the material. If that material is not conducting, then you would not have any losses. That means whatever is the decrease of energy stored in magnetic fields and electric fields, that same decrease would be transferred to the next region. But if you have ohmic losses, some energy would be lost in conduction. This E bar cross H bar is called as Poynting vector, and this is called as the Poynting theorem. This is named after the scientist J.H. Poynting. This concludes our current module. These are the references, the wave friends and the phase friends I have downloaded from this source, and for our general discussion I have followed Elements of Electromagnetics by Matthew Sadico. Thank you for your attention. We'll meet you in the next module. For any queries, please ask in the comment section. Thank you.